بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. I would like to welcome my students from grade 12 into the first online lesson regarding probabilities. Now these lessons are going to be from chapter 3. We have been delaying these lessons a little bit because we were not sure about the ministry's decision of what topics are cancelled. But since we don't have any word from the ministry until now, and since we only have 1 month and a half until the exams, so I think it's better that you take these lessons now. They're not many. I think they're going to be 5 or 6 videos at most for both chapter 3 and chapter 4. These two chapters are quite small chapters and I think they're easy. But we will start today with the first lesson, and we will start on this topic of probabilities from the very beginning. So let's see. Okay, so the first lesson of this chapter is going to be about some fundamental probability theorems. We will study mainly 4 theorems of probabilities with some results, and we will also talk about some of the axioms of probabilities. So by the end of this lesson, you should be able to, these are the lesson objectives, you should be able to identify the probability axioms, and we will know now the meaning of axioms and what are the probability axioms. The second objective is to prove the probability of theorems. You should be able to prove each theorem of the 4 theorems, and you should use the probability theorems and axioms as well to calculate the probabilities of events. Okay, so these are the main objectives of this lesson. If you get these 3 objectives, then you got the main point that we want to explain. Okay, before we start with the whole topic, let's talk a little bit about probabilities. And to speak about probabilities, there are 2 terms that I need you to differentiate between. These 2 terms are the probability experiment and the probability event. Okay, so the first thing that we need to discuss is the differences between probability experiments and probability events. This is even before we start with the theorems and before we start with the axioms. Now, let's look at this table in this example. In this example, I'm going to give you a probability experiment, and then I'm going to list some probability events from that experiment. I want you to differentiate between the 2 things. It's really important that you know these 2 things pretty well. And I'm going to give you this example and one more example, and mainly these 2 examples are the main examples that you deal with in grade 12. So the first experiment that I'm going to talk about is throwing a fair die. Okay, so I think many of you know what a fair die is. So it's something like this. This is a fair die, and you have here some dots indicating numbers. So for example, this side is 5. For example, this side is 4, maybe. Okay. And for example, this side is 3. Okay. And of course you have other sides. You have 2 and 1, of course, as well. So this is a fair die, right? I think many of you have seen this. Many of you have even played with this. We usually use this to select a number randomly from 6 possible numbers. So what are the possible outcomes? The question here is what are the possible outcomes of this experiment? Okay, so again, guys, look at this. Throwing a die is called a probability experiment, okay? And any probability experiment must have a list of possible outcomes. All the possible outcomes, a set of all the possible outcomes of this experiment. Now, when you throw 1 die, what results do you expect? Well, I think it's easy to know that I'm going to expect one of these numbers, either 1 or 2 or 3 or 4 or 5 or 6. Can we expect anything else other than these numbers? For sure, no. These are the only numbers that we can expect from throwing a die. It's either it's going to land on, and the face on top is going to be 1, or it's going to be 2, or 3, or 4, or 5, or 6. A die has only 6 faces, and we only have 6 possibilities. So these are called the possible outcomes. This set is a set of all the possible outcomes, right? This set here is actually a set of all the possible outcomes. Now, this set is quite important for our example now. Why? Because this set has a special name, and we call this set the sample space. Again, this set is called the sample space. And the sample space is always given a symbol, and that symbol is S. So what is the sample space? The sample space is the set of all the possible outcomes of an experiment. It's a set in which we collect all the possible outcomes of an experiment. So in our case, the sample space is this set, which is from 1 to 6. Okay? Now this is an experiment. What do we mean by an event? Now look at this. We can have an event like the one on the right, which is the event of getting an even number. Okay, what do we mean by an event? Now you're going to throw a die and you're going to get 6 possible answers, right? So you're going to get 1 of 6 possible answers. How many of these answers can be an even number? Or what answers of these are even numbers? Can you get an 8? Can you get a 10? Can you get a 0? Of course no. So what is the outcomes can you have, and these outcomes are even? I think you might say that the event of getting an even number, we can get an even number if we get a 2, or if we get a 4, or if we get a 6. But we can't get any other number, right? Now we call this an event. We call this an event. Now notice that the event is only part of the sample space. So the sample space is from 1 to 6. These are all the possible outcomes. The event is part of them. And usually the event is given a capital letter, like A or B or C or D. So this is event A. So if we say A, what do we mean by it? We say A, we mean that it's the event of getting an even number. Of course, you can call it whatever letter you like, and you can have whatever event there is. Now I want you to notice that the event A, just use a pen here. So the event A is actually a subset of the sample space. This sign here means subset or part of. So this set is actually part of the sample space. Okay, let's look at another event. So another event, the event of getting an odd number. Okay, so this is completely different. I'm going to call this event with a letter. I'm going to give it a letter. So let's, for example, give it the letter B capital. This event of getting an odd number is actually going to include the following numbers. Odd numbers are either 1 or 3 or 5. So these are the 3 possible odd numbers we can get out of this experiment. This is now another event. If this is event number 1, this here is a second event, or event number 2. And also notice that this event, which is B, is also part of S. Okay. A third example is the event of getting a prime number. So what's the prime number? A prime number is a number that can be divided only by itself or by 1. A prime number is a number that has 2 factors. So what are the factors of 1? The factors of 1 is 1. It's only 1 factor, so it's not prime number. What are the factors of 2? You have 2 factors of 2. It is 1 and 2. Itself and 1. 3 also, itself and 1. 4 has 3 factors. 4 can be divided by 1 or by 4 or by 2. So it has 3 factors, so it's not prime. 5 has 2 factors only, itself and 1. 6 has 4 factors, 1, 6, 3 and 2. It can be divided by 1 or by 6 or by 2 or by 3. So this is not prime. 4 is not prime, 1 is not prime. So what are the prime numbers? The prime numbers are going to be 2, 3, and 5. So let's call this event C, C capital. And we'll also notice that this event, which is event number 3, is going to be part C is going to be part of S. So it is a subset of S, right? Now notice that all the events we're talking about are subsets of the sample space. They're part of the sample space. So finding the sample space at the beginning of the question is quite important, because when you find the sample space, it's like you found the container that contains all the possible events there are in the question. Now one might ask a question, are these the only events that we can get from this experiment? Actually not. We can get a lot of other events as well. We can say there is an event of getting a number that is less than 2. We can say that there is an event of getting a number that is a multiple of 3. We can say that there is an event of getting a number that is more than 6. In this case, we will have nothing in that event. It's going to be 5. We can say that there is the event of getting a number that is divisible by 4. We can get only one number. All of these events, what is important to know is that all of these events, A or B or C and D, so whatever number of events you have, together all of these events, they make something that is called omega. Okay, so what is this omega exactly? Omega, so omega is called the event space, and the event space is always given this symbol. So this is the space in which we can collect all the possible events that are possible from an experiment, that we can get from an experiment. Okay, so as I'm telling you that we don't have only these events, we can have a lot of other events. You can use your imagination, and but all of these events can be collected in one place, and that place is called the event space. So we call this the event space. Okay, now, so this is an experiment, a probability experiment, and that is a probability event. Now it's really important to relate what we have just taken now with something that we have taken before in grade 9, which is how we draw sets using what we call Venn diagrams. Now you see, we have 3 circles here with this big rectangle, and our intentions are to draw these numbers on these circles. So let's see. So we have an event. The first event is called A, and it contains 2 and 4 and 6. So we can give it this circle, for example. So we can say that this circle is A, And we say that what's inside of it is 2, 4, and 6. We have another event, which is B, and inside of it we have 1 and 3 and 5. So inside of B, we'll notice that A and B have nothing in common. So that's why I'm going to draw B in that separated circle. And it's going to contain 3, 5, and 1. Now again, notice that B has nothing in common with A. However, if we put C here in the middle, now it all falls into the right place, right? Because what is common between C and A, what is common between C and A is the 2. You see the 2 here, and the 2 here is the same number. So this place actually is common between both C and A. Let's highlight it. This place here is common between both C and A. It is this 2 along with this 2. Okay, what is common between B and C is the 3 and the 5. So the 3 and the 5 here, the 3 and the 5 here. This is common between B and C. So that's why we put it here, in the space between B and C. That's common between them. Okay, and we must notice, I must insist that you notice that A and B are totally separated from each other. So now the following is going to be important. Look at this, guys. First of all, we say the following. We say that A intersection with B. This simple intersection means common. What is common between A and B? Sometimes, or most of the time in grade 12, we write this as AB only. We don't write the intersection sign, but we mean A intersection B. We mean what is common between them. So what is common between A and B? We notice that there is nothing common between them. Phi. Okay? So we notice that these two sets are totally separated from each other. So they are separated. Nothing is common between them. So when two sets are separated, then this makes their intersection becomes phi. There is nothing common between them. Okay. What about what is common between A intersection C, right? Or we can call it AC. So what is inside of AC? We will notice that we have one element only, which is 2. Okay. What about B intersection C or BC? In BC, we'll notice that we have 2 elements, which are 3 and 5. Good. What is A union B? A union B. Union means both of them together. So both of the two sets together. We collect everything inside of A, and we collect everything inside of B, and we write them together in one set. And we don't repeat anything if it's repeated. So A union B will be 1, 2, 3, 4, 5, 6, right? This is going to be A union B. What about A union C? You'll notice that A union C, A and C is going to be 2. I'm not going to repeat the 2 again. 3, 4, 5, 6, right? So what does the union mean? The union means the two sets together. The intersection means what is common between them. So when I write BC, when I write AC, I mean what is common between them. When I write A union C, I mean both of them together. When I write AB, I mean what is common between them. When I write A union B, I mean we collect them both together. I hope that this is clear so far. Notice that AB is phi. We call the two sets separated. Actually, we have another important name for it. We call them mutually exclusive. I'm going to write a note here. If two events, A and B, if their intersection is equal to phi, there is nothing common between them, then A and B are called mutually exclusive. We call them mutually exclusive. This name is important. Mutually exclusive. So whenever you hear this name, you must know that their intersection is equal to 0. There is nothing common between them. Good? I hope that this is fine so far. So in this example, we have seen 3 events, right? Now, I have put the 3 events in a circle, in 3 circles, as I've shown you now. But what about this big rectangle? What does it represent? This big rectangle actually represents everything there is in the sample space. So the sample space contains everything inside of here. It is 1, it is 2, it is 3, 4, 5, 6. And if there was something extra in the sample space that is not in the events, I was going to write it here outside. So this is how we represent our events using Venn diagrams. Okay. So far we've seen a probability experiment. We have seen probability events. What about calculating the probability itself? Now, every probability system is composed of 3 things: the sample space, the probability event, or the event space, right? The event space, or the probability event. And the third thing is the probability function. This probability function is given the letter P. So here, another note, probability function. So the probability function. What's the probability function? A probability function is actually given the letter P, which we define it as the following. We said the probability of an event, any event, whether it was A, or it was B, or it was C, or maybe it was AB, because this is an event as well, or maybe it was AC, or maybe it was BC, or maybe it was A union B, or A union C. All of these are events. Every set is an event. The probability of an event is equal to the number of the elements inside of the event over the number of the elements inside of the sample space. This is now an important rule that we will deal with in this lesson, but we will deal with extensively in the coming lesson. It's called the probability function. Every probability system is composed of 3 things: the possible outcomes, or the sample space, the event space, or the probability event space, and this is number 2, sorry, and the third thing is the probability function. So every probability system is composed of these 3 parts. What do we mean by the probability of an event? Look at this, guys. Let's come back to these events, to these 3 events. First of all, the event of getting an even number. If I want to calculate the probability of A, what I should do is I should count how many elements are there in A. So how many elements are there? There are 3 elements. So I'm going to write 3, and then I'll divide it by how many elements I have in the sample space. So how many elements I have in the sample space? I have 6 elements. I can cancel this with this. I will get 1 over 2. And what does this mean? It means that when I throw a die, a fair die, there is half the chance that I'm going to get an even number is 50%. Half. Half is 50%. So the chance I'm going to get an even number is 50%. The same thing when you throw a die and you're expecting to get an odd number. So the probability of an odd number, you can see here. So the probability of an odd number, probability of B, is equal to the number of the elements inside of B, which are 3 elements, over the number of the elements in the sample space, which is 6. This is also half, which means that you have 50% chance of getting an odd number if you do this experiment. So the probability of this event is 50%. You can do the same thing with C. You can even do the same thing here. So you can, for example, find the probability of AC. What is the probability of AC? How many elements are there in AC? You have 1 element, and you divide it by 6. So there is 1 over 6 chance that you're going to get A and C together. You're going to get an even number and a prime number at the same time. There is only 1 chance, because the only number that is both even and prime is 2. So this is the probability of A and C. The intersection means and. The union means or. So the probability of getting, let's not do this one, let's do the other one. The probability of getting an even number or a prime number is 5 over 6. You see 5 elements, 2, 3, 4, 5, 6, 5 elements over the total number of elements, which is 6. We'll see more examples like this in the coming lesson, inshallah, and I think that we're going to get it even better. Let's look at another experiment. So, another experiment that is quite important for grade 12 is the experiment of tossing coins. You might have only 1 coin or maybe 2 coins, regular coins. So if you're tossing a coin, you either have one of these 2 chances. You either get a head or you get a tail. What if you throw 2 coins together? So if you throw 2 coins together, what is your sample space? What are the possible outcomes? Let's see. The possible outcomes is that you're going to get a head from the first coin and you're going to get a head from the second coin. That's one possibility. Look at this, guys. You're tossing 2 coins together. So you either get head and head from both of them, or you maybe get head from the first coin and tail from the second, right? Or maybe you're going to get a tail from the first coin and a head from the second. Or maybe you're going to get a tail from the first coin and a tail from the second. These are 4 possible outcomes that you may, and these are all the possible outcomes that you might get from this experiment. This is the sample space. What is the number of elements in the sample space? The number of elements in the sample space are 4. 1, 2, 3, 4. Each ordered pair is counted as 1 result. So either head from the first coin and head from the second coin, or head from the first coin and tail from the second, or tail from the first and head from the second, or tail from both. So there are 4 possibilities here. What events can we derive from this experiment? Look at this. We can get, and this event, the event of getting 2 heads. Okay, we can define this event as A, so we can give it the letter A, and it will contain only 1 element, which is head from the first coin and head from the second coin. That's only 1 element. Getting 2 heads. I'm getting 2 heads from both of them. That's an event that contains only 1 element. What is the probability of A? It's the number of elements inside of A over the number of elements inside of S. How many elements are there inside of A? It is 1. How many elements are inside of S? There are 4. So there is a 25% chance that I'm going to get 2 heads at the same time. What is the probability of getting 1 head and 1 tail? So let's call this event B, and we want 1 head and 1 tail. So it's either you have head from the first and tail from the second, like this picture, or you can get a tail from the first and a head from the second. So that's one tail and one head. One tail, one head, one tail, one head. So what is the probability of this event B now? The probability is the number of elements inside of B over the number of elements inside of the sample space, which is going to be 2 over 4, which is 1 over 2. So there is a 50% chance that you're going to get one head and one tail. Okay, so what is the probability of getting 2 tails? We can call this event C. 2 tails, so tail from the first and tail from the second. And the probability of C is going to be the number of the elements inside of C over the number of elements inside of S, and that is going to be 1 over 4, because this is only one element here. There's only one element here, so this is a 25% chance. Now, notice that these 3 events are actually, all of them are mutually exclusive. There is nothing common between these events. So event A and event B are mutually exclusive together, and event B and event C are mutually exclusive together. So A, B is equal to phi. Nothing is common. B, C is equal to phi as well. Nothing is common. And A, C is equal to phi. Nothing is common. So A and B and C, all of them are mutually exclusive. We mean with mutually exclusive, they're separated from each other. Good? I hope it is. So this was now an introduction to probabilities. So what is probabilities? This is what I want you to understand now. What do we mean by probabilities? What is the sample space? What is the probability function? And what is the events space? The events space is now, for example, in this example, the event space, which is called omega, is actually all the possible events, A, B, C, and any other events I can think about. All of these events are called omega, which is the event space, okay, or the probability event space. So we have now the 3 components, of any probability system, which are the sample space, the event space, and the probability function. Okay? Okay, so now let's now come into the first important part of this lesson, which is the probability axioms. What do we mean by axioms? The word axiom means a fact that does not need to be proven. So if you have a fact and that fact does not have to be proved, this fact is called an axiom. So the first axiom in probabilities is that for any event that is A, which is part of the event space, omega, then the probability of A is more than or equal to 0. It means it's a positive number. So any probability, in other words, any probability must be positive. Not only positive, it must be less than or equal to 1. So any probability actually should always be more than 0, positive, and less than 1. So probabilities are always fractions between 0 and 1. You can have a probability of half, you can have a probability of 1 over 4, of 2 over 4, of 3 over 4, 2 over 3. You must always have a probability that is between 0 and 1. And we've seen this in the previous examples. And that is our first axiom. The second axiom is that if you have an S, which is the sample space, then the probability of S is equal to 1. This should be a common sense fact, because the probability of S is equal to the number of the event. What is the event in our case? It is S over an S in the denominator. Remember that here we have the event and here we always have S. If the event is S, then we have S over S. If we cancel them together, we get 1. So the probability of S is equal to 1. This is called a sure event or a certain event. It's not that hard to understand. I'll just explain it to you with the example that we've taken before. Now, in the problem of the die, when we had a die, the sample space was equal to what? It was equal to 1, 2, 3, 4, 5, 6, right? If I define an event and I tell you I want an event of getting a number less than 7, what are you going to call this event? Call it A. Okay, what numbers less than 7 you can get from here? All of them. You can get 1 or 2 or 3 or 4 or 5 or 6. So if I tell you, you throw this die and I want you to get a number less than 7, you will say, this is a sure event. For sure I'm going to find a number less than 7. I'm going to throw the die and 100% I'm going to get a number less than 7. This is a certain event or a sure event. The probability of A in this case is going to be the same as the probability of S, because A and S are going to be equal, and in this case, going to be 1. So the probability of S is always equal to 1. We call S a sure event or a certain event, and any event that looks like that, it has a probability of 1, is called a sure event. The third axiom says the following. If A and B are two mutually exclusive events, so mutually exclusive means that they are separated, then the probability of A union B equals probability of A plus probability of B. And this is also easily seen with the first example that we've taken. Remember that we had A and B. A was even numbers and B was getting odd numbers. So even numbers were 2, 4, 6. Odd numbers were 1, 3, 5. What is the probability of A? Even numbers. It will be 3 over 6, right? Because there are 3 numbers and the sample space is 6. And it was half. The probability of B was the same thing, 3 over 6, which is half. Now, if we aside here, if we talk about A union B, what is A union B? A union B are the two sets together. So it's going to be 1, 2, 3, 4, 5, 6. What is the probability of A union B? It will be the number of sets in A union B, which is the number of elements, which is 6, over the number of the elements in the sample space, which is 6. So this is 1, right? If we actually take the probability of A plus the probability of B and we add them, we will get half plus half, which is also going to be 1. So the axiom says simply that if your events are mutually exclusive, then A union B is equal to probability of A plus probability of B. However, I want you to notice something, that this is a special case only. This rule can be applied only if you have two mutually exclusive events. So if you have two mutually exclusive events and we ask you for probability of A union B, you can just take probability of A and add it with probability of B. But if they are not mutually exclusive, then we're going to take a general formula for A union B with one of the theorems. So now let's move on to the probability theorems. The first theorem. So there are 4 theorems. We will learn how to prove them. We will use the axioms actually to prove them. And then we will take some examples or exercises on the theorem. This lesson is going to be quite long. So if you feel tired, if you feel like you need a break, you can always pause the video. Just remember where you paused and take a break, come back to it, and study it again. If there is a part that is not clear, please repeat it until you get it well. You can always ask me as well. And I encourage you to have a copybook and a pen and write these down, because when you write them, you get them better. Okay, the first theorem says the following. It says the probability of any null or impossible event is 0. The probability of any null or impossible event is 0. Or that is, the probability of phi is equal to 0. How do we prove this? Let's show you how do you prove this. So prove. Now look at this. If I look at phi and the sample space, phi means nothing and the sample space means everything. What is the intersection between them? What is the common between them? Phi, look at the example that we've taken before. We said that phi was actually phi is nothing, right? And the sample space was 1 and 2 and 3 and 4 and 5 and 6. If I ask you, what is phi intersection with the sample space? What is common between them? You will simply say that there is nothing common between them. It is phi. So phi and s, these two events, we can call them they are mutually exclusive events. Aren't they mutually exclusive? Because there is nothing common between them, so they are mutually exclusive. They're separated. We said if there is nothing common, they're mutually exclusive. The third axiom says the following. It says the probability, so therefore, the probability of phi union s is equal to the probability of phi plus the probability of s. Right? The probability of phi union s, because the third axiom, just to remind you of the third axiom said the probability of A union B, it doesn't have to be A and B, it can be any other letters. So A union B, phi union s equals the probability of phi plus the probability of s. Right? So this is from the third axiom. This is axiom 3. Okay. What is phi intersection s? We said phi intersection s was phi. What is phi union s? When we say the union, we just bring everything. So 1, 2, 3, 4, 5, 6, isn't it? So isn't this s? It is the same, right? So if we come back here, phi union s is the same as the probability of s. So probability of s is equal to probability of phi plus probability of s. We've just learned that the probability of s is equal to 1, so we can substitute here 1 equals probability of phi plus 1 as well in the other side. Let's move this together. So 1 minus 1 equals the probability of phi, or we can say that the probability of phi is equal to 0. And that's the proof, QED. It's a simple proof. It will never change. It's always the same as this. You start from two mutually exclusive events. You use the third axiom, and then probability of s is equal to 1. Make probability of phi the subject, and you're done. Let's see the second theorem. So the second theorem says the following. The probability of A complement equals 1 minus probability of A. So what is this dash here on top? This is called the complement. The complement means when something, the opposite of an event. So if you have an event here, for example, if you have the sample space, and you have an event A, and let's say this event A is getting a number less than 3. Let's say that the experiment was throwing a die, so the sample space is 1, 2, 3, 4, 5, 6. And let's say that we have an event A, and let's define it as getting a number less than 3. So what are the numbers less than 3? They're 1 and 2, right? So A is going to be 1 and 2. Sorry. So 1 and 2. This is going to be A. A prime, or A dash, is called the complement of A. What is the complement of A? It's the opposite of this. So what is the opposite of getting a number less than 3? It's getting a number that is equal to 3 or more. So the opposite is 3, 4, 5, 6. It's everything that is not inside of A. And where is the place of these numbers? They're actually outside, right here, 5 and 6. So here what's outside, what is shaded now, here is actually what? This is A dash. So we can say simply that A dash is not A. Let me ask you a question. So we can say that the probability of an event the probability an event might not occur, like A dash does not happen, the opposite of A. So we say the probability it is less than 3 is 1 and 2. What is the probability that this does not happen? We don't get something less than 3. The probability is 3, 4, 5, 6. So it is 4 over 6. So we say the following. We say the probability that an event might not occur, does not happen, is equal to the probability that this event occurs, happens, subtracted from 1. So we take 1 and we subtract minus the probability of A. Let's prove this. Look at this, guys. A and A dash. What is common between them? What is common between this set right here, which is A, and the other set, which is A dash? What is common between this set and this set? Is there anything common between this one and this one? There is nothing common, right? Actually, A intersection with A dash is equal to phi, nothing. There is nothing common between them. So are they mutually exclusive? Yes. So A and A dash are mutually exclusive. If they are mutually exclusive, then we can apply the third axiom with them. So the probability of A union A dash is equal to the probability of A, the first one, plus the probability of A dash. Okay? Now let's ask a question. What is A union A dash? Look at the two sets there and make a union for them. You'll get 1, 2, 3, 4, 5, 6. Right? Isn't this the sample space, all of it? It's actually, yes, it is the sample space. So if we come back here, the probability of A union A dash is the same as the probability of S. So the probability of S is equal to probability of A plus the probability of A dash. Now we want to make probability of A dash the subject. We will move this here. And the probability of S is equal to 1. So 1 minus the probability of A is equal to the probability of A dash. And that is the second theorem proved. Okay? So therefore, the probability of A dash is equal to 1 minus the probability of A. Guys, you can write this theorem in 3 ways. You can write this theorem as follows. Probability of A plus probability of A dash equals to 1. That's one thing. Or you can say probability of A dash equals 1 minus probability of A. The same way it's written above. Or you can say even probability of A equals 1 minus probability of A dash. From here, just making the subject either A, or you can move A dash and make A the subject. So you can write this theorem actually in 3 different ways, and we will see how do we use each one of them in different questions. Okay, so this is theorem 2. Let's move on to the third theorem. So the third theorem says the following. The probability of A B dash is equal to probability of A minus probability of AB. Or in words, we say the probability event A occurs and B does not. So A occurs and B does not, equals the probability of the occurrence of both A and B together subtracted from the probability of the occurrence of A. Okay, to see this clearly, I think we will need to use a Venn diagram. So let's do that. Look at this, guys. If I have a Venn diagram like this one, let's say that I have 2 events, and these 2 events are A and also B. I wanted to understand the theory before we prove it. So this is B, this is A. And the whole thing for sure is the sample space. Let's say that we're talking about throwing a die. So the sample space is the numbers from 1 to 6. 1, 2, 3, 4, 5, 6. Let's say that event A is getting something less than 3. So what is event A? It is going to be 1 or 2. Let's say that event B is getting something even. So getting something even. So B is going to be 2 or 4 or 6. Good. Now, what are we going to write here in the middle? We're going to write 2 because it's common between the 2 sets. What do we still have in A? We still have 1. What do we still have in B? We still have 4 and 6. What do we still have in the sample space? We still have 3 and 5. It's going to be outside of this region. Now look at this, guys. I want you to pay close attention to the following, because understanding these ideas is going to make a lot of questions a lot easier for you. Look, this place, which is now highlighted in yellow, this place is actually called, only the place highlighted in yellow, is called A and not B, like this. This place is A and not B. It means this place is a number less than 3, A, and not even, not B. 1 is a number less than 3 and not even. So this place is called A and not B. This complement, the dash that we have seen in theorem 2, is actually pronounced as not. So this is A less than 3, and the intersection means and. So A less than 3 and not even. Okay, this place right here, let's highlight it with this color. This place, this is not a highlighter, let's use the highlighter. So this place, this place right here, this place actually is called AB. Let's write it with a pen. So this place is called AB. Here, this is AB. Okay, let's use a different color. Again, this place is called AB. Why do we call this place AB? Because this number 2, is less than 3 and even. Remember that the intersection means and. It is less than 3 and even. So this place is both A and B. The third place, so maybe we can write them here now. We can say the following. AB dash is actually 1. Less than 3 and not even. AB less than 3 and even is 2. The third place, so let's use a highlighter. The third place right here, what do you think this place is? This place, the third place, is actually, it is B, right? It is inside of B, but not inside of A. So it's BA dash. This third place is BA dash. And what do we mean by that? I mean even and not less than 3. It is even, these numbers are even, and they are not less than 3. So this place is 4 and 6. The ones outside here, the ones outside, okay, here, the 5, the 3, and the 1, 5 and 3, and that's it, right? 3 and 5 only, yes. The 3 and the 5, the ones outside, these actually are, they are not A and not B. What does that mean? These actually, they are not less than 3 and not even. So they are A dash and B dash. And what is it? We have there 3 and 5. Okay? So we have 4 different regions now in this drawing. We have AB dash, which means less than 3 and not even, which is 1. We have AB in the middle, which means less than 3 and even, which is 2. We have 4 and 6, which is BA dash, which means even and not less than 3. 4 and 6, even and not less than 3. And we have the place outside, the 2 circles, which is not less than 3 and not even. So it is A dash and B dash. These are 4 important different regions in this drawing. This drawing is an important one. If you get this, you will get a lot of things in probabilities. And a lot of these theorems depend on this drawing. Now, how do we prove our theorem on top using this drawing? This is quite easy. You can see from the drawing, you can see actually that, let's make sure that this is a pen, yes, okay. So we can see from the drawing that AB dash and AB, you see AB dash, that part, the yellow part, and AB, the green part, they are mutually exclusive. What do we mean by that? What is AB dash intersection with AB? What is common between them? Look at the sets. There is nothing common between them, so it's fine. So they're mutually exclusive. If they are mutually exclusive, then this means the probability of AB dash union with the AB is equal to the probability of AB dash plus the probability of AB. This is, again, the third axiom, which changes the union into plus. Okay, from the drawing, look at AB dash union AB. Look at this. What is AB dash union with AB? What if we unite them together? You can look at the sets or you can look at the Venn diagram. If you unite them together, you'll get 1 and 2, right? Isn't that the same as A? Actually, it is. So if we come back here, AB dash union with AB is actually equals to A. You can look at it from the Venn diagram, you can look at it from the sets, It all checks out. So this means that this is the probability of A equals probability of AB dash plus the probability of AB. Let's make probability of AB dash the subject. So the probability of AB dash is equal to the probability of A minus the probability of AB. And it's really very clear from the drawing. If you want the yellow part, you will have all of A, okay, the circle, all of the circle, and you will minus the green part. So it's going to be A minus AB. And the same thing if you want the orange part. So also, you can also conclude that the probability of BA dash, the orange part, is going to be the probability of all of B minus the probability of AB. And you can memorize this rule as follows. The probability of A, B dash, if one of them has dash, then you start with the one without the dash minus both of them without dashes. A, B dash, the one without the dash, minus both of them without dashes. B, A dash, the one without the dash, minus both of them without dashes. So this is the third theorem. We will have some results on this theorem actually. This theorem is so important, we'll have some results on it. The first result is the following. If A and B are two mutually exclusive events, then probability of AB dash is probability of A, and probability of A dash B is probability of B. Please concentrate on these results because they usually come as they are in the ministry exams. Let me show you how. You have to know how this happened. Look, if A and B are two mutually exclusive events, so these are A and B, they're two mutually exclusive events. They're separated from each other. Then they say the probability of A, B dash equals the probability of A. Let's prove it. According to the theorem, probability of AB dash is actually probability of the one without the dash minus the probability of both of them without dashes, right? This here, the probability of AB itself is equal to phi. There is nothing because they're mutually exclusive, they're separated. And the probability of AB is the probability of phi. And the first theorem says the probability of phi is 0. So this means that this is probability of A minus 0, which is going to be probability of A. So the probability of A, B dash is equal to the probability of A. And that is the first part right here. The second part is quite the same thing. If you want to prove the second part, probability of B, A dash is equal to probability of the one without the dash minus the probability of both of them. The probability of both of them is actually the probability of phi. And the probability of phi is equal to 0 because they are mutually exclusive events. That's why it is phi. And probability of B minus 0 is probability of B. So probability of B, A dash is equal to probability of B. And that is our second result. And please, guys, concentrate on this because it usually comes as true, false, or fill in the blanks in the ministry. We'll look at the second result. So the second result says the following. If given that B is subset of A, then the probability of AB dash is equal to probability of A minus probability of B. And also, the probability of A dash B is equal to 0. So let's look at this one. B is a subset of A. I advise you that whenever you have a case like this, it's always good to draw it. So I'm going to draw two sets. I'm going to draw A as a small circle here, and I'm going to draw B as a bigger circle right there. So I'm sorry, it should be the opposite. B is part of A, so B should be inside, and A should be outside. So this is B, and this is A. Now this is a case in which B is part of A. Now you can think of it like this using sets. You can say that B, for example, is 2 only, okay? While A is 1 and 2 and 3. So now B is part of A. B is 2, while A is 1 and 2 and 3. So B is part of A, okay? AB. What is common between A and B? You'll notice that what is common between A and B is actually going to be this place. This place is going to be common between A and B, which is in numbers, this is 2. And that means that AB is equal to B, which is the smaller set. This only happens if one of them is part of the other, subset of the other. What is A union B? Now A union B is going to be this set A with this set B, all of what is set A and all of set B. So the union of the two sets is going to be 1 and 2 and 3, right? And this is going to be A, which is the bigger set. Okay, now taking this knowledge with the theorem that we have just learned, we've just learned that probability of A B dash is equal to the probability of the one without the dash minus the probability of both of them, A, B. So the probability of A as it is minus the probability of AB. Now we have seen that AB is the same as B. So the probability of AB is going to be the probability of B. And we are going to get this first result right here. And when we want to get the second result, we'll do the following. We say the probability of A dash B is equal to the probability of the one without the dash minus the probability of both of them without dashes. Now this is the probability of B minus the probability of AB again, guys, is the probability of B, the smaller set. Probability of B minus probability of B becomes 0. So the probability of A dash B is going to be 0. 0 means that this is an impossible event, right? What is exactly impossible? It is impossible to find something, look at this, guys. It is impossible to find something in B that is not inside of A. It is impossible to find something in B that is not inside of A. Look at the drawing. You cannot find something inside of B but not inside of A. You cannot do that. That's why the probability is 0, or this is an impossible event. So whenever there is a subset relationship, I always advise you to draw something like this one, like the drawing that you just made. And with this drawing, maybe you can use some numbers. It's random numbers, it's fine, it doesn't matter. Okay, so let's move to the fourth theorem, and the most important one and the last one, which is the following. For any two events, A and B, the probability of A union B equals the probability of A plus the probability of B minus the probability of AB. Now look at this, guys. We have seen this before. We have seen the probability of A union B before in the axioms, but this was for a special case. In that case, A and B were mutually exclusive. But this time it says for any two events. So this formula now is a general formula. This is a general formula for any two events. The probability of A union B is the probability of A plus the probability of B minus the probability of AB. Let's prove it. But before we prove it, let's have a picture of it. So this is how it looks like. Let's bring an example that is similar to the previous example. This is a sample space. Now we have these two sets. Let's call this A. Let's call this B. We have seen previously that this part here, the crescent-like part, this part is actually, it can be called, this part is A and not B. This part is A and not B. It is what is inside of A but not inside of B. This part in the middle, the yellow part, this part was called AB. So this part here is AB. So this part is both A and B, right? The third part, the part which is right here, it's not a highlighter. So the third part, which is right here, this part with the dark blue, this part actually is called B and not A. Let's try it again. This is B and not A, right? The whole thing together now, the whole picture in front of you, is actually A union B. The three colors together is A union B. So you can say that A union B is equal to A B dash union with AB union with B A dash, right? You can say that. You can say that this is equal to AB dash union AB union B A dash, the three parts together. So this means that the probability of A union B is equal to the probability of A B dash union AB union B A dash. Good? Now I want you to notice that these three events, AB dash and AB and BA dash, the three of them, all are mutually exclusive. They are all mutually exclusive because there is nothing common between them. Each part is completely separate from the other. So this means that if they are mutually exclusive, I can change the union into plus. So this is going to be probability of A B dash plus probability of AB plus probability of BA dash, right? This is here the probability of A union B. Now this is a formula that we have taken in Theorem 3. So probability of A union B equals, here we will use the one without the dash first minus both of them. This is here, instead of this one. Plus probability of AB as it is. Plus here we will use Theorem 3 again. So it is the one without the dash minus both of them. Now what do you notice? There is a negative probability of AB here and a positive probability of AB here. They can cancel each other. So we will get probability of A plus probability of B minus probability of AB. So this is going to be the probability of A union B, and this is quad erat demonstrandum. And this is the proof of Theorem 4. So we've seen now 4 theorems with some results. We can continue with more results now on Theorem 4. So let's see that. So the first result on Theorem 4. For any two events A and B, the probability of A union B equals probability of A plus probability of BA dash. Again, they're all clearer with the drawing. If you put the drawing here, these are the two circles. This is A, this is B. This theorem says that the union is the same as the same as A, all of it. So this is all of A. Do you see? All of this circle is A. Plus B and not A. This place is B not A. Right? These are two mutually exclusive events. So the theorem says simply if you add them together, you will get the probability of A union B. And it's true. This place is A and this place is B A dash. Together, A union B is going to be A union B A dash. And since they are mutually exclusive, we can change them into what? Into addition. When we put the probability function to both sides, we can change the right side, the right hand side into addition. So this is the first result. The second result says the following: A union B equals B plus AB dash. It's quite the same thing. Let's bring the drawing. So it's quite the same thing. So if this is B and this is A, now look at this, guys. So he says here that A union B is equal to B, so this is B, plus AB dash. AB dash is this part, A and not B. So AB dash. And actually, of course, this should be seen as right, because if this is A, B dash, and this is B, A union B will be actually B union AB dash. And these two events are mutually exclusive. If they are mutually exclusive, it means that we can change the union into addition when we put the probability function. So if you put the probability functions of both sides, it's going to be probability of B, change this, probability of AB dash. And that is your second result. And the third result is that probability of A union B is probability of AB dash plus probability of BA dash plus probability of AB. And this is what we have depended on when we started proving the previous theorem. We said it's AB dash and AB and BA dash. That's the first line actually in our proof. So that is the third result. Okay. So here we will see a summary of all the rules. So this is a summary of all the rules. And this drawing again, which is an important drawing, which shows us AB dash, AB, BA dash, and this part outside is A dash, B dash, which is equal to A union B all dash. Now, let's explain this part first, but before that, let's look at the table. So the table contains rules for one event, rules for two events, and rules for three events, or for two mutually exclusive events. Here, any two events, but here, two mutually exclusive events. The axioms, first of all, for one event, the probability of A is more than 0, so it should always be positive. This is what we said in the axioms. The probability of S is equal to 1. Sample space is going to be 1. It's a sure event, or a certain event. For two mutually exclusive events, as an axiom, we said that the probability of A union B equals probability of A plus probability of B. So the union changes into addition. Okay, so these are the axioms. The theorems. The first theorem said that the probability of phi is equal to 0. We call this a null event or an impossible event. Probability of A dash was equal to 1 minus probability of A. And from here we saw that the probability of A plus the probability of A dash is equal to 1. Or we said also that the probability of A is equal to 1 minus probability of A dash. Right? So the probability of not an event is equal to 1 minus the probability of the event itself. If you have two events, then the probability of AB dash is equal to the one without the dash minus both of them. And also we have seen the probability of A union B, which is probability of A plus probability of B minus probability of AB. We said that this one is general while this one is only for mutually exclusive events. We have seen some results. Probability of A union B, we have seen 3 results for it. AB dash plus B, BA dash plus A, and AB dash plus ABA dash plus AB, and they're all clear from the drawing. You can get these 3 results from the drawing. Just remember the shading parts, just add them. And we said here that if they are mutually exclusive events, probability of A B dash is equal to probability of A, and BA dash is equal to probability of B, because when we subtract the minus AB from probability of AB, this is actually the same as this rule here. When you subtract AB, because they're mutually exclusive, this is going to be 0. So you'll get only probability of A and probability of B. I hope that this is clear. It's not that hard. Practice these rules well. We still have one more rule in this chapter, and that's it. These are all the rules that we will see in this chapter. Let's take some exercises. So this is the first exercise. Given that the probability of A is 0.5, the probability of B is 0.3, the probability of AB is equal to 0.1, calculate A, probability of A union B, B, probability of AB dash, and C, probability of A dash B dash. Okay, yes, reminding me of something. Now here, look at this, guys. This actually is a rule that you took in grade 9 that we call De Morgan law. What does De Morgan law say? It says if you have A dash intersection with B dash, then this is going to be A union B all dash. If you have a complement or a knot of A and B, and there is an intersection between them, you can change it into union and make a complement at once. Or we'd like to write it like this: A dash B dash, this means intersection. If we don't write anything, it means intersection, equals A union B all dash. We use this a lot to solve a lot of problems in this chapter. There is another one, but it's not that important in grade 12. There is A dash union B dash equals AB all dash. But it's not really important in this lesson. What is mainly important is the first one. So let's look at this exercise. This is a question in which direct substitution will work. Just write the rule and use direct substitution. Probability, so A, let me use another color. Let's erase this. So let's use the blue color. So A, they want us to find the probability of A union B. According to the fourth theorem, sorry, this is going to be the probability of A plus the probability of B minus the probability of AB. And guys, I have all of these in the question. They're given to me. So it's 0.5 plus 0.3 minus 0.1. Just add them. 0.5 plus 0.3 is like 5 plus 3 is 0.8. 0.8 minus 0.1, the answer is 0.7. That's it. That's the answer. It's quite easy. Just you must know the rule. If you know the rule, everything is easy. Part B, they want the probability of AB dash. So the probability of AB dash is the probability of the one without the dash minus the probability of both of them. The probability of the one without the dash is A. A is 0.5 minus the probability of both of them is 0.1. It's also given in the question. And the answer is 0.4. So that's part B. Part C, the probability of A dash B dash. We actually don't have a rule for this. So what are we going to do? We'll use De Morgan. We will change it into A union B all dash. Now, we know that the probability of A dash is 1 minus probability of A, right? We know that this applies also if there is B. This also applies if there is anything else. Like if you have AB all dash, it's going to be 1 minus probability of AB. If you have probability of A union B all dash, it's going to be 1 minus probability of A union B. It applies all the time. for any event. So this is the case I have here. So this is going to be 1 minus the probability of A union B. I have found this before in part A. It's really important in probabilities that you try to solve the questions in order, because sometimes you will need the answer of A in C or in B. And you need to be careful, because if you made a mistake in A, you're going to make a mistake at C as well. So here is going to be 1 minus 0.7. So you think of 1 as 1.0, it's 10. 10 minus 7, you get 0.3. So 1 minus 0.7 is not negative 0.6. That's wrong. This is a whole number. This is a decimal number. So you make it decimal as well. So it's 1.0 minus 0.7, which is 10 minus 7, which is 0.3. So the answer is 0.3. I hope that this example is easy enough. Let's do another example. So given that probability of A is half, probability of B is 1 over 4, and the probability of A union B is 2 over 3, calculate the probability of AB and the probability of A union B dash. Let's check this out. So let's start with part A. We want the probability of AB. Now there is no rule for probability of AB. We don't have a theorem that says that gives us the answer to probability of AB. But we have a relationship between probability of AB and probability of A union B. This is theorem 4. We know that the probability of A union B is equal to the following. It's equal to the probability of A plus the probability of B minus the probability of AB. Now look at this, guys. We know this one. It is 2 over 3. We know that the probability of A is half. We know the probability of B is 1 over 4 minus probability of AB. We don't know this one. So this is AB. Because this is negative, I am going to move it to this side to make it positive, make it the subject, and then move to over 3 to the other side. So the probability of AB is going to be equals to 1 over 2 plus 1 over 4 minus 2 over 3. Now we must make this the same denominator. I think making it 12 is going to be good, because all of them is divisible by 12. So multiply by 6, multiply by 6. Here we multiply by 3, multiply by 3. And here we multiply by 4, multiply by 4. So what are we going to get now? So the common denominator is going to be 12, right? We'll have 6 in the numerator plus 3 minus 8. 6 plus 3 is 9, minus 8 is 1, so the answer is 1 over 12. So this is the probability of A, B. And the last part, part C, we want the probability, the part B, it is part B. We want the probability of A union B dash. Now it might seem like we don't have a rule for this, but we actually have. This is the same as theorem 4, which means that this is going to be the probability of A plus the probability of B dash, because this is B dash, minus the probability of AB dash. AB dash. Okay, so just replace A by B by B dash. It's the same as this rule, but just write, instead of B, write B dash. Now, this is going to be probability of A, which we have, plus probability of B dash. We don't really have it, but I know that it is 1 minus the probability of B, isn't it? Minus probability of AB dash. I don't have it, but I know that it's equal to the one without the dash minus both of them. Good. So I'm substituting the rule inside the rule, and it's totally fine, no problem here. The probability of B dash is 1 minus probability of B. That's theorem 2. The probability of AB dash is probability of A minus probability of AB. That's theorem 3. I've just put them inside of theorem 4. I'll open the brackets now. So this is probability of A plus 1 minus probability of B. I'll multiply this second bracket by minus, so minus probability of A plus probability of AB. Notice that now negative probability of A and positive probability of A cancel each other, and we will get 1 minus probability of B. I have it, it's 1 over 4, plus probability of AB. I also have it, which is, I've just found it, which is 1 over 12. This denominator is 1, and to make the denominators the same, I'm going to multiply by multiply here by 12. So multiply here by 12, and here by 12, here by 3, and here by 3. So I'm going to have the common denominator, which is going to be, in my case, 12 as well. So this is equals to 12 in the denominator. In the numerator, I have 12 minus 3 plus 1. So 12 minus 3 is actually 9. 9 plus 1 is going to be 10 over 12. So the answer here is going to be 10 over 12. Sorry for that. So the answer again is going to be 10 over 12. I hope this one is also easy. And let's move on to the third and the last exercise. Given that the probability of A is x, the probability of B is 1 over 3, and the probability of A union B is 2 over 3, calculate the value of x if A and B are mutually exclusive. And the second thing, if B is part of A. Okay, this is easy. It's not hard as well. But here you have to understand that we have two different cases, two different scenarios. So the first scenario says that A and B are mutually exclusive. This means that AB is equal to phi. And it means that the probability of AB is equal to 0 because the probability of phi, which is 0. I have the union. I'm given the union. So I can use the probability of A union B. Because they are mutually exclusive, I'll use the axiom. So it's equal to probability of A plus probability of B. Even if I use the general rule, minus probability of AB is minus 0. So it's not important, write it. Probability of A union B is 2 over 3 equals probability of A is x plus probability of B is 1 over 3. So we want to find x. We will transpose this here. So 2 over 3 minus 1 over 3 is equal to x. So this means that x is equal to 1 over 3. So this is the value of x if they were mutually exclusive. The second part is not related to the first part. So they want us to calculate x again, but this time with B as part of A. If B is part of A, then AB, the intersection, is going to be the smaller one, which is B. And A union B is going to be the bigger one, which is A. Right? We said this just earlier, 2 slides ago. We said the intersection is going to be the smaller one, and the union is going to be the bigger one. Now notice that what we want the probability of A, which is x, right? So the probability of A is going to be the bigger one. So the probability of A is going to be the probability of A union B. We have A union B, it's 2 over 3, and this is x. So in this case, x is equal to 2 over 3. And that's it. Knowing your rules well and knowing how to use them is the most important thing in probabilities. The rules are really easy. They're not many, by the way. And if you just have them pictured in your head, they're going to be a lot easier. So whenever you're stuck with probabilities, just draw, and drawing is going to get you away. I'm going to leave this one as homework for you. It's not going to be hard. It's actually somehow of a direct substitution. You're going to use the results there. I will need you to try this, please, and have them answered in the paper and send them to me. And for extra exercises, you can check page 133 in your book. And I wish you the best of luck. In the next class, inshallah, we will talk about the second lesson, which is the construction of a probability model. It's going to be a lot easier than this lesson, I promise you that. and there are no new rules in that one. In the third lesson, we'll have 2 more rules, and that's it. So this chapter is going to be only 3 lessons, and I hope that we're going to finish them in 3 videos. Until then, I wish that all of you are safe and sound, and I really hope that I'm going to see you soon, and peace.